All right, good afternoon, everyone. Hello again, my name is still Iris. I want to talk a bit about radio transients, and the original title I proposed was radio variability with ASCAP and LOFAR, but I've changed that a little bit because I think this might be a more interesting talk for this audience. So I want to talk a bit about multi-wavelength follow-up of radio transients and the other way around. So radio follow-up of optical multi-messenger high energy transients. Yeah, I mentioned this before, but I'm an Osgraph postdoctoral researcher based at the University of Sydney. So to give a bit of an outline, I first want to talk about, so I've divided this talk in two parts. I first want to talk about how do we follow up transients that we identify in the radio. And I've sort of made this division into slow and fast radio transients. I'll explain that later. And then the second half of the talk, I want to talk about how we use radio facilities to follow up optical, multi-messenger, or high energy transients. So to give a bit more detail, from the radio transient perspective, I want to detail how we identify these radio transients and how we study them. And then the slow ones I want to talk about are mainly your typical synchrotron transients. And for the faster ones, I want to highlight this specific new example that we found, which are the long period radio transients, which I think are really interesting. And then the radio follow-up of other transients, I want to highlight some specific examples where I think radio has been proven very successful to contribute some sort of unique perspective to our understanding of these systems, focusing on recurrent novae, GW170817, because why not, and gamma ray bursts. Right, so there are several approaches in trying to detect radio transients, and one of them is through dedicated surveys. These are actually quite rare, but one I'm working on is called the Variables and Slow Transient Surveys, or VAST, which is a survey science project that runs on ASCAP, the Australian Square Kilometre Array Pathfinder. So ASCAP is a radio telescope. It consists of 36 12-meter dishes, like shown in the top right, spread out over Western Australia. And the plot below shows the sort of coverage that we have with VAST. So VAST covers the part of the galactic plane, and it observes the galactic plane at quite high cadence, once every 2 weeks. But we also observe quite a large portion of the extragalactic sky, which we revisit once every 2 months. So currently we're halfway through the survey. VAST started in 2023, and we've now had 2 years of observations. So it's time to do some digging into what's actually in there. So I'm focusing on the extragalactic part of VAST. I'm preparing a data release for that. And since we started observing 2 years ago, we now have roughly 10 to 12 observations per extragalactic field, as shown in this plot. And since you're not all radio astronomers, I brought this plot from the paper I'm preparing to sort of highlight the sort of sources that we find if we do a variability study in this data set. So since most radio sources are AGN, also most variable radio sources are AGN, and we have a good chunk of radio stars, we find pulsars that are variable. So these, I want to highlight that we do not detect the individual pulses of pulsars in a survey like this, but we detect the scintillating pulsars or the pulsars that are in binaries that might be eclipsing. So pulsars not only show variability on millisecond timescales, but also on these longer timescales. And then we have a small slice of other sources, which are probably some of the most interesting ones. So to give an example of a slow radio transient, I want to highlight one of these sources from this blue other slice. So a source that we found that was highly variable in VAST, I show the light curve here, so this is the radio light curve, is a supernova candidate. And I'll talk a little bit about why I've labeled it a supernova candidate. So the radio light curve here, there's only non-detections before the VAST survey starts. So this is really something that emerges in the radio and then is quite radio bright for roughly 2 years. And these units might not make sense to you, but 4 to 5 millijansky is really quite bright. And when we look at the location of that radio source and overplot that on an optical survey, you see that there is an optical counterpart. This is a dwarf galaxy here at a photometric redshift of 0.03, which seems to be associated to this radio source. So assuming that distance, that implies a peak radioluminosity of 10 to the 29 ergs per second per hertz. Now, we also found an optical transient at this location, which is labeled a supernova candidate. So there's only 1 or 2, I think, CTF detections in the different images. I show one here. So it's really sort of a marginal candidate. It's most likely a supernova. But it's very interesting that if this is really a supernova, it seems to be optically very dim. But in the radio, it seems to be very, very bright. This is one of the brightest supernovas detected in the radio, if this is really associated to that dwarf galaxy. So a really interesting source, and one that we're following up currently, first of all, mainly with other radio instruments to try to get some idea of the spectrum of this source, but potentially in the future, if this proves indeed an interesting source, we of course want to confirm the redshift of that dwarf galaxy, for example. All right. Another way to identify radio transients is through commensal searches. So if we have radio astronomers that are looking for H1 absorption and they want to stare at a patch of sky for 8 hours, then that's great for them, but it's also great for me because I can piggyback on those observations and look for the transient sources in that observation. Yeah, I want to highlight the high time resolution imaging aspect of things, which is a really recent development in the radio. So if we have that 8-hour observation, we can now divide those 8 hours up in 8-second snapshots. Something that has maybe been done for a long time at other wavelengths, but this is really a computational challenge at radio wavelengths, but it allows us to do things like what's shown in the GIF and really find things that flare, show flares in the radio with the duration of only a minute or so. I just want to mention that technique is complementary to beamform searches. So those are the ways we find FRBs and pulsars. So those are really transients on millisecond timescales. And what we're trying to do here is really quite different. We're making images at second timescale resolution. To sort of highlight that point of how recent that development is of high time resolution imaging searches, I've just listed some of the pipelines that are available for different instruments. And if you just look at the years of when those pipeline papers were published, you can see that that is really only been happening over the last couple of years. And a very cool result of some of those pipelines is that we've been able to find a new class of radio transient sources. So these are what I call the fast transients. They show flares with durations of a couple seconds to minutes. And these bright radio bursts repeat with periods of minutes to hours, which is why we have given them the unimaginative name long period radio transients. So the first thought, which also shows the bias of radio astronomers, I guess, is these must be pulsars. These are things that repeat in the radio. However, most pulsars have periods of a fraction of a second or so. So how do we make a pulsar that spins so slowly that it only emits a pulse once every couple of hours? So that hypothesis has not been completely disproven, but we've shifted a bit from just this slowly spinning pulsars idea to saying, okay, probably, or actually a good fraction of these long period radio transients are actually N-dwarf, Y-dwarf binaries. And I mention this example here because really it is through multi-wavelength observations that we've been able to confirm that. So we see the optical counterparts of these sources, which are faint M-dwarfs. We do photometry to find that there is a blue excess and that there is a white dwarf. We do spectroscopy to confirm the orbital parameters of the system, and so forth. And also some of these systems are actually X-ray bright. So it's really a whole range of multi-wavelength observations that allow us to fully characterize what these sources are. All right, then I want to focus on the vice versa bit in the last couple minutes. So the radio follow-up of optical multi-messenger high energy transients. And I think you could say that this is probably more the traditional approach, or how radio observations have been used, because in these typical synchrotron transients, you have the radio emission always appear at later times. And that's how we've traditionally maybe used radio. Yeah, to highlight the power of radio observation, I've just picked a few examples. So we have RSO Fuki, which was already mentioned before. This is a recurrent nova system consisting of a white dwarf accreting from its companion. Once the white dwarf has accreted enough material, you get this thermonuclear explosion on the surface of the white dwarf, which really causes this really ridiculous brightening in the optical. And these systems are very interesting because these might be type 1a supernova progenitors. And they also teach us a lot about potentially the maximum mass of the white dwarf. So the most recent outburst of this system was in 2021. And here I show again the optical light curve, but there was really a wide range of multi-wavelength follow-up. So I think it was already mentioned in the context of X-ray observations. I don't have those on this slide, but I do have the high energy observations, where for the first time we detected these high energy gamma photons from a recurrent nova system, allowing us to say something about the potentially hadronic or leptonic scenarios. And then in purple, I've highlighted the radio observations. So by making these detailed radio light curves, we can model them. We can model these detailed radio light curves, say something about the circumbinary density around these nova systems, which tells us something about the mass loss rate. We can model the ejected mass during this nova explosion, which tells us something about, is the white dwarf actually accreting matter, or is all that matter that is accreted expelled during a nova explosion? And also, if you do a high resolution radio observations, like done here with VLBI measurements, you can really map the outflows. So you can really say something about the 3D density distribution around these nova systems. I think in the interest of time, I might actually skip over this one and go straight to the short gamma ray bursts. So again, we use radio observations of short gamma ray bursts to probe this afterglow emission. So this interaction of expelled material with a surrounding medium. But also in the case of short gamma ray bursts, we might expect some prompt coherent radio emission. So in this cartoon here, which I won't detail too much because I think Antonia might talk about it, there are different places in this binary neutron star merger process where you might expect coherent radio burst to appear. However, if that coherent radio burst is emitted during the in-spiral or just after the merger, you really want to start your radio observations as quickly as possible after you've detected the short gamma ray burst. So you need rapid response modes on your radio telescopes, or ideally you even need an all-sky monitor in the radio that is just looking everywhere all the time. All right, just to conclude, so for the first part of the talk, this multi-wavelength follow-up of radio transients, I think we have a bit of work to do in order to fully exploit the next generation of radio telescopes, like LOFAR 2.0, the SKAO, NGVLA, or DSA 2000. I think we still need to improve our detection algorithms, looking for radio transients, and improve the turnaround time between actually detecting them and creating a transient alert. And for the second part of the talk, which I think we're all facing, radio follow-up of multi-wavelength transients, given these new facilities that come online and will produce millions of transient alerts, we only have limited radio follow-up facilities. How do we identify the most promising events? And maybe the most promising events are different at different wavelengths, as in maybe the radio can contribute more uniquely to some sources than to others. So these are all questions we can think about. And yeah, I just want to say I'm excited to learn from all of you and collaborate with transient astronomers at other wavelengths this week. Thank you.